Hello dear students, this is José de Jesús García Rubalcaba, lecturer at UABC. In this short lesson, we will learn about local extreme values for functions of several variables. First, some reminder of your previous courses. From algebra, you know the proper values of a square matrix. They are the solutions of the characteristic polynomial. This is a polynomial of degree n, which corresponds to the size of the matrix, and its solutions are the proper values. The matrix could have complex components, but in this case we will need only real components. Also, a reminder from your first calculus class. We begin with a function that is differentiable at least 2 times. If we have an extremum, it could be a maximum or a minimum. Then the first derivative is 0. In this case, we talk about a critical point when the first derivative is 0. If it's a maximum, then the second derivative is less or equal to 0. In a minimum, the second derivative is greater or equal to 0. In the other direction, if we have a critical point and the second derivative is negative, then we have a maximum. And if we have a critical point and the second derivative is positive, then we have a minimum. Another reminder from the previous unit, the gradient. It's a generalization of the first derivative for functions of several variables. It's just the transpose of the Jacobian matrix. In this case, it's a column vector. And the Hessian matrix, we need the function to be twice differentiable for our purposes. It has the second partial derivatives. It's the Jacobian matrix of the gradient. And if the function can be differentiated at least 2 times, then we know that it must be a symmetric matrix. What we are going to do is to take the proper values of the Hessian matrix. It is a symmetric matrix, and from the spectral theorem we know that all its proper values are real. That means that the imaginary part of them is always 0. Since they are real, we can think whether they are negative, 0, or positive. When all the proper values are positive, then the matrix is positive definite. The matrix is negative definite definition is that all the proper values are negative. Now this A is positive semi-definite. It means that no proper value is negative. Some could be 0, some could be positive, perhaps they are all positive or 0, but none of them is negative. And negative semi-definite means that none of the proper values are positive. Finally, if no proper values are 0, then A is definite. Perhaps some are negative, some are positive. Let's think again about this function that is twice differentiable. We can think whether it has a local extrema. If we have an extremum of f, it could be a maximum or a minimum. Then the gradient, which corresponds to the first derivative, must be 0. It is a critical point that the gradient is 0. In a maximum, then also the Hessian matrix, which corresponds to the second derivative, is negative semi-definite. No proper value is positive. In a minimum, the Hessian matrix is positive semi-definite. In the other direction, if the gradient is 0, that means that we have a critical point. And the Hessian matrix is negative definite, then we are in a maximum. If we are in a critical point and the Hessian matrix is positive definite, that means that all the proper values are positive, then we have a minimum. This is a graphical example of a maximum for a function of two variables. This point corresponds to a maximum, and this is a minimum. Here this vertex is a minimum of a function of two variables. But perhaps the Hessian matrix has some positive and some negative proper values, both positive and negative. What happens there? We have what is called a saddle point. That's the name of these critical points, when there are some positive and some negative proper values for the Hessian matrix. And here we see graphically a saddle point for a function of two variables. Here, in this bird, we have a critical point, but it's neither a maximum nor a minimum, because it has one positive proper value and one negative proper value. Now, a simple example. Consider this function. This is a function of three variables. It's a polynomial actually. And we have to find its critical points first, and then we have to find out what they are, maximum, minima, or saddle points. First, to find the critical points, we must compute the gradient. Here it is. I will return one slide. You can write down this function. Please compute the gradient. Compute the gradient, and then check out if you got the same answer as here. And then we must solve this equation. We equal the gradient to 0 and solve the equation. In this case, it is a very simple equation. In most cases, it can be somewhat more difficult. But this one is straightforward and has two solutions. -1, 1, 1, and 1, 1, two different solutions. It will not always be this easy. Also, from here, from the gradient piece, now compute the Hessian matrix. You can stop the video, compute the Hessian matrix, and then check out if you were interrupted from the next slide. Here is the Hessian matrix. I hope you have computed it yourself. In this case, it's a diagonal matrix. It's a very simple case, and we know that in the case of a diagonal matrix, the proper values are just the components from the diagonal. It will not always be a diagonal matrix. Usually it will not be. And now the first critical point that we found, -1, 1, 1, we compute the Hessian matrix there. We only have to evaluate, and we get this matrix. It's a diagonal, and all its proper values are negative. All of them. Then this point is a local maximum. This matrix is negative definite. This is a critical point. The Hessian matrix is negative definite. Then we have a maximum. The second critical point, this 1, 1, 1, compute its Hessian matrix. Some proper values are positive and some are negative. We have both positive and negative. This matrix is definite because no proper value is 0, but some are negative, some are positive. Then this point is a saddle point. It's a critical point. It's a saddle point because the Hessian matrix has some positive proper values and some negative proper values. I hope you have enjoyed it, and until then.